Uh, can everyone see my screen? Can you hear me? I'll assume that's a yes. You can hear me?
Yes.
Okay, thank you. Just wanted to make sure before I start going. Thanks for having me. My name is Nate Steinle. I'm a postdoc at the University of Birmingham. I'm going to talk with you all about the Bardeen-Petterson effect and supermassive binary black holes today. And this is a drawing of a binary black hole. There's a separation distance between the two holes. Each has its own spin angular momentum, and each has its own spin orbit misalignment. If I talk about the spin, I'll probably be talking about the dimension, the spin magnitude chi. There are two kind of broad classes of formation channels for supermassive binary black holes, which are known as gas-poor, gas-rich galactic hosts. And various processes drive the in-spiral, kind of color-coded by this figure here, where at the largest separations, the angular momentum loss of the binary is driven by dynamical friction. And then at smaller separations, scattering of individual stars through the loss cone of the binary begins to dominate. And then at even smaller separations, the viscous drag from a disk migration phase will dominate if the binary is in a gas-rich environment. And then the baton finally gets handed off to the gravitational wave emission phase, driving the binary to merger. And the LISA mission should be able to observe gravitational waves from these supermassive binary black hole mergers and discriminate between the two formation channels and probe all this complicated physics. And so loss cone scattering of individual stars is known to create roughly isotropic spin directions, theoretically. So for binaries that evolve in gas-poor hosts, those isotropic spin directions will remain roughly isotropic through the gravitational wave phase, implying that the spin precession of binaries in gas-poor hosts will be generic, meaning that the orbital angular momentum L will precess and nutate. In our model, we're going to examine binaries that evolve in gas-rich hosts. And we're just going to assume for simplicity that the evolution begins after loss cone scattering, meaning that the initial angles are isotropic. In these gas-rich hosts, the binary experiences disk migration through a circumbinary accretion disk, where the kind of as shown in this cartoon on the bottom right, the binary carves out a cavity in that big circumbinary accretion disk, and little mini disks or secondary disks form around each black hole, from which the black holes actually accrete from. And this accretion can align the black hole spins by the Bardeen-Petterson effect, which is essentially a combination of lens-Turing precession and viscous interactions, and it's complicated. But basically, the inner region of the disk aligns to the equatorial plane of the black hole quicker than the outer region of the disk, which is working to align the black hole spin with the orbital angular momentum of the circumbinary disk. And that effectively creates a warped structure of the accretion disk. And if the warping is substantial enough, depending on the parameters that govern the disk profile, the disk can actually break at a critical angle. And in our model, we assume that if we encounter a critical angle, that the alignment ceases for the rest. If the alignment ceases and the angle is just held constant for the rest of the disk migration phase. So on to the results of our model. We have the disk migration phase and then the gravitational wave phase. This is the theta 1 is the misalignment of the more massive black hole, and theta 2 is the misalignment of less massive black hole. And this is the evolution of these angles through the in-spiral of the binary. And each color corresponds to a different binary here. It's just pairs of angles here. And we're only varying the initial spin misalignments here. All the other parameters of this model, which I don't have time to go through right now, are held constant. So we're only varying the initial angles right here. And if the black holes are initialized with a spin sufficiently above the orbital plane, then the spin gets aligned rather quickly due to the Bardeen-Petterson effect and stays aligned once the disk migration ends and at the transition between disk migration and gravitational wave phases, which occurs at the decoupling separation, where the binary's orbital the binary's orbital momentum decouples from that of the disk. But if the spins are initialized sufficiently below the orbital plane, then the spins can be aligned partially, and then they reach a critical angle, which, like I was saying, we just hold it to be constant thereafter until the gravitational wave phase. And then if the spin directions are initialized sufficiently near the orbital plane, then the binary then the black hole, basically the disk around the black hole just starts at a critical configuration, and the angle does not evolve through the disk migration phase. Putting those two plots together, you get this scatter plot of cos theta 2 versus cos theta 1 for a larger population of binaries. And each red dot is the initial spin orientations. And so each binary evolves from a red dot along a blue line to a blue cross at the end of disk migration. So we're not looking at gravitational wave emission here, just disk migration phase. And there's a general trend from kind of like the bottom left to the top right of this plot, which should make sense because the Bardeen-Petterson effect is an alignment process. There's kind of distinct regions of binaries here. And so binaries in the top that start out with spin orientations in the top right corner or region of this plot get both of their black hole spins aligned and end up at the very top right corner. Binaries in the bottom right region that start in the bottom right region only get the primary black hole spin aligned. Binaries that start out in the top left region only get their secondary spin aligned. Binaries that are initialized in this little black box that I have imposed on this figure start with their disk migration at a critical configuration, so their misalignments don't evolve during disk migration. And binaries in this kind of larger orange box I made here, this contains the region of binaries that avoid complete alignment of either black hole. So both spins are misaligned. And that region is occupied by about 35% of the binaries in this case. And so we have at most 4 subpopulations here, whether the spins are both aligned, only one was aligned, or both remained misaligned at the end of disk migration. And if we look at the fractional contribution of each of those 4 subpopulations, color coded here in this plot, if you look at them as a function of alpha, which is the dimensionless viscosity parameter, the blue region corresponds to binaries that have both spins misaligned at the end of disk migration. And for smaller values of alpha, the smaller values of alpha correspond to less viscous disks that are more prone to breaking, and hence more binaries encounter a critical angle, and the fraction that have both spins misaligned is therefore larger. That's why the blue region is so large at small alpha. And then in the limit of large alpha, you have more viscous disks that are less prone to breaking, and more binaries are aligning. And these fractions basically converge to about a quarter, because that little black box that I showed you before has shrunk to like the center of that scatter plot, which basically just cuts the plane in quarters. And last but not least, after disk migration, you have the gravitational wave driven phase, where the spin orientations here evolve through the post-Newtonian inspiral on lines of constant aligned effective spin chi effective. And so here's our scatter plot again, with these green lines now superimposed on top of the blue crosses, which shows that the binaries will evolve. Each binary evolves on its own green line here of constant chi effective. And you can see this is a further complication for these subpopulation fractions, making some of them larger or smaller, perhaps, and effectively making these subpopulations functions of the inspiral. These are preliminary results that hopefully will be published very soon in Im and Ross, so keep your eye out for it. And to summarize, binary black holes in gas-rich environments will likely experience disk migration and accretion, where the Bardeen-Petterson effect creates subpopulations depending on the spin orientations of the black holes that are dependent on the parameters of the binary black hole and on the disk profile parameters. And each of these subpopulations can result in different predictions for spin precession. And gravitational wave emission can further complicate these subpopulations, which will be important for observations of LISA, by LISA of these mergers. And hopefully LISA will be able to probe these subpopulations and therefore the complicated physics of disk migration and accretion, which I think is really cool. And some other work I'm currently working on, I'm looking at implications of including higher gravitational wave multiple modes on LISA observations, and I'm looking at how the ejected mass of black hole neutron star binaries depends on high black hole spins. And thank you so much for listening. I'd love to have any questions now.
Okay, I think very quickly I have one question. So you say obviously your focus here is on populations for LISA, but are there any implications for LIGO and to the populations that we've already seen of BBHs and the spins of those populations? Do they line up with what you would expect from this, or is it again too early to really relate what we have at the moment with your work?
So I guess that would be kind of relevant in a scenario where, you know, the stellar mass black holes that LIGO can see have evolved in some kind of accretion disk. I know there has been, right, as I understand your question, I know there has been some work on the accretion disk, the AGN channel formation for stellar mass black holes, and the Bardeen-Petterson effect might play a role, but I'm not sure about that. Because this is kind of like a distinct astrophysical environment necessarily, you know, where you have, you know, the big disk and the mini disks. But surely, yeah, spin precession and precession of, you know, the precession of an accretion disk could very well be important for stellar mass binary black holes that evolve in accretion disks, for sure.
Yeah, thanks. Sorry, that was a bit of a stinker of a question.
That's fine.
Okay, thanks very much.